Hi, my name is Pulivarthy. I worked with Dr. Manoj Karki this summer at CPAS, and with my mentor Achit Paudel to complete the autonomous navigation system of the Warthog vehicle through orchards. Did you know that according to a 2022 study, autonomous orchard vehicles can reduce labor costs by up to 30% and increase efficiency by 20%? There are significant economic benefits to autonomous orchard vehicles, such as higher efficiency, but there are also benefits for farm workers. Health risks increase due to high temperatures during certain times of year. Additionally, there's a growing demand for food as the population rises, but a falling supply of farm laborers, especially year-round laborers. There's a significant gap in the research for fully autonomous orchard navigating robots, which can help meet this rising demand by taking on a number of tasks like pruning flowers, harvesting fruit, spraying fertilizer, and other procedures that would traditionally take a lot of time and manual labor. I use two major simulation tools in this project, Gazebo and Arviz. Gazebo is a simulation environment for testing robots, and it can simulate uneven terrain, inconsistent plant growth and row patterns, and other important factors that we could encounter in a real orchard. I didn't get a chance to test this project extensively in a real-life orchard, so the demos you'll see today are simulation only. I hope we can recreate these results at one of the orchards around Prosser in the future. RViz is a powerful visualization tool for robot and sensor data. The image to the top shows the perspective of the warthog as it traverses the simulated orchard, and the image to the bottom is a visualization of the sensor data from the warthog, which is collected by the LiDAR sensor. The warthog was chosen for its robustness and its ability to carry heavy loads, making it an ideal choice for things like autonomous fertilization. The LiDAR sensor on the right is what was visualized in the previous slide. So the LiDAR sends out pulses of light to measure distance on an approximately 2D plane and gives a point cloud that can be used as a depth map for different objects in the distance. Devin Beeler started working on this project last summer as an Ag 8 intern, and he achieved fully autonomous navigation within a row. For this demo and future ones, I'm going to speed it up to 2 times speed for the sake of time. But anyway, he focused on tracking the location of the trees in the surrounding rows and adjusting the warthog's location to stay approximately in the center of each row. So you can see there was a bump there in the right row, and the warthog adjusted itself to maintain its distance. His work was the foundation of pretty much everything I did this summer, so I want to give a major thank you to Devin. My personal additions to Devin's work include improving the in-row path planning to be more robust and adding the ability to turn into new rows. For path planning during the turn, I found that the relationship between linear velocity, angular velocity, and radius for a particle could be applied to the Warthog effectively. The Warthog is a skid steer vehicle and obviously not a particle, so there are deeper kinematics we could get into. But for the speeds relevant to this project, which are all under 1 meters per second, that wasn't necessary. When calculating the angular velocity and duration of the turn, I used the same linear velocity value that the Warthog was moving at throughout the row. And for the radius, I had to keep track of the approximate distance between the Warthog and each side of the row to get an average row width. Dividing that value by 2 gave us an approximate radius for the semicircle that the Warthog would have to move in to complete a turn. There are other ways to turn into a row, such as by taking a sharper turn, but I felt that a semicircle was efficient enough and it would put the least strain on the turning mechanism of the Warthog. I tested this program at speeds between 0.1 and 1 meters per second, but for most commercial applications, there's usually no need to go faster than about 5 meters per second, or sorry, 0.5 meters per second. Most of the challenges I faced working on this project were LiDAR related. For example, the LiDAR had a tendency to lag or send old data during the turn, which would throw off the navigation for the next row in the orchard. Additionally, the LiDAR inherently has a limited field of view and is more susceptible to noise compared to an RGB camera. Because LiDAR just measures distances using light pulses, it can't differentiate between soft and hard obstacles like grass versus a human. As a result, if the grass is overgrown in a particular area of the orchard, the LiDAR might detect that as a potential collision and stop the warthog. This is exacerbated by the fact that the LiDAR is positioned relatively low on the actual warthog. One last challenge was unreliable IMU and odometry data. So these sensors would have made tracking the absolute position of the warthog in the orchard much easier, but they had problems with drift over longer time periods and distances. This wasn't a concern moving through one row, but when we turn into new rows and move further and further away from the starting point, the data becomes unreliable. I worked around these problems in a number of ways. To reduce the quantity of LiDAR data and process it more easily, I clustered points that were approximately in the same area, and rather than treating each individual coordinate as a separate piece of data, I also filtered out a lot of the LiDAR data that was outside of the required field of view. To reduce the program's susceptibility to noise, I averaged the LiDAR data throughout the row and used this mix of data for path planning rather than only relying on data from that point in time. Finally, if the warthog isn't deep enough in a row to collect sufficient data, I would just move it forward slowly until it got enough, and if it has to turn slightly, then it can do that as well. Oh, and this was a demo on the side of the turning mechanism, a little bit of a closer view, and also what the terminal view is like, so what direction it's turning, the offset, and the position. Sorry, that's offset and position from the center line, by the way. All right, finally, here is a complete demo of the warthog traversing the orchard. Again, I'll turn the speed up. And yeah, so while this plays, I want to briefly mention some of the ways to improve and build on what we have right now. Most importantly, this system can be made much more robust by incorporating an RGB camera and an image segmentation model. So that would allow the warthog to differentiate between soft and hard obstacles, and it would also be able to identify the end of the row more consistently. As it stands, a mid-sized gap between trees on one side of the orchard can trigger the turning mechanism because with only LiDAR, there's no way to be certain when you're at the end of a row. And you can see sometimes there are gaps between trees in the simulation. I got around that by just increasing the field of view a little bit, but that does decrease the overall uh, ability of the warthog to stay at the center of the row. Other improvements could include dynamic turning, and what I mean by that is the Warthog could use the LiDAR data as it turns into a row to automatically adjust its turning parameters, and it would more consistently turn right into the center of the row. But as it stands in my simulations, the Warthog sometimes turns into the new row and then has to adjust itself as it begins moving forward. Thanks again to my mentor, Achut, and my PI, Dr. Karki, for this project, and thank you to CPAS and AgAid for hosting me this summer. Thank you.